This episode is sponsored by Ren, a website where you calculate your carbon footprint, and you can also sign up to make a monthly contribution to offset your carbon footprint or support rainforest protection projects. When you are in the world of the microbes, it does not seem necessary to think of the largest land mammal on Earth. What could elephants possibly have to do with a ciliate? When you say this out loud, any potential connection seems dubious at best. However, if you look at the Dileptus, you see an elongated, moving body, one that seems like it's made up entirely of snout, like an elephant's trunk, disembodied and shrunk down so that it can survive all on its own. But unlike the elephant, Dileptus is no gentle giant. It isn't moving around because it wants to play or drink water. No, the Dileptus is waving around because it is loaded with toxins and it wants to put them to good use. Now, this may be surprising given its general blob-like appearance, but the Dileptus's body is divided into two distinct regions, the proboscis and the trunk. But the trunk on the Dileptus is not actually the elephant trunk-like part of the organism. The trunk is in this case more like the trunk of a tree. It's the base for the rest of the Dileptus's body. The proboscis is the snout, the part that extends to the rest of the microcosmos and examines it looking for something to eat. And interestingly, where the proboscis and the trunk connect lies the Dileptus's mouth, a cavity lined with hair-like cilia that continues down the length of the proboscis. The Dileptus can use these cilia to generate currents in the water that carry food to its oral cavity. You can imagine it a bit like if your arm hairs could stir up the air around you and levitate the snack in your hand all the way to your mouth. Which, now that I'm thinking about it, sounds amazing. But before the cilia can work their magic, the Dileptus has to catch its food. And that's unfortunate for the sporostomum at the bottom left corner. It does not know that on the other side of that piece of debris is a predator that one scientist called the king of beasts among the ciliated protozoa, with an appetite that is, quote, insatiable. The Dileptus is not a subtle, lying-in-wait kind of predator. It's always moving, always seeking, and when its proboscis makes contact with the sporostomum, it grabs a chunk of its body almost instantly. The sporostomum is large and nimble and pulls away quickly as if it's been stung, but it leaves behind a tasty morsel of itself, which the Dileptus draws in until it's close enough to open wide and eat. And from its safe distance away, the sporostomum may not be whole again yet, but it is at least out of reach of the Dileptus and of its proboscis and its hundreds of toxicists. You can actually see those toxicists here when we look at the proboscis with 1,000 times magnification. And while the proboscis's movement through the water may seem like a chaotic mess of twisting left and right and up and down, there is a surprising order to it all, driven by the placement of those toxic cellular weapons. The Dileptus has to move in a way that lets it immediately attack its prey upon contact, but its proboscis is only lined with toxicists on one side, the side that leads to the oral cavity. So it always sweeps its proboscis with its toxicists facing whatever is about to be swept. And when it's done moving in one direction, the Dileptus rotates its proboscis and sweeps it in the other direction. Again, this is also that when the Dileptus finally hits something, it won't just make contact, it will unload needles full of toxins into whatever it has made contact with. To learn a bit more about how these toxins work, in one experiment, scientists filled a fluid with the material coming from the Dileptus's toxins. They then placed some paramecium into the fluid to see how they would respond. They did not respond well. Immediately, the paramecium tried to mount their own defenses by releasing their own harpooning trichocysts. Now that might have worked against an actual Dileptus, pitting ciliate against ciliate as they poke each other for survival. But in this experiment, with the toxins permeating the fluid, the best the paramecium could hope for was to delay the inevitable, to use its trichocysts as a temporary fence until, eventually, it emerged to its own death. Now that is an extreme situation, one that a paramecium would probably not actually find itself in were it anywhere else but in a lab. Fortunately for paramecium, we do not live in a world full of Dileptus toxin fluid. Those toxins are kept safely packaged within the organisms themselves, waiting for their designated time. Which does lead us to a final question, one that we do not have an answer for, but that we like thinking about nonetheless. We've seen the Dileptus as a solitary organism, and we've also seen it in groups with others of its kind. But how? How does an organism that is so simple, so reactive, so toxic, how is it able to just casually entwine itself with others of its own kind? How can they gather without immediately all jabbing each other to death? Well, we don't know. But it means that there must be more to the release of toxicists than just the simple mechanical stimulus of touch. That there must be some sort of recognition that makes it possible for two Dileptuses to know each other. You might even call it chemistry. Now, we don't know the underlying signs and signals that make that recognition possible, but what drove this mutually assured safety may have actually been something selfish. Imagine for a moment that the palm of your hand was covered in toxic needles, and every time you touched your own body, your palm tore off a piece of it. You would probably not last long as an organism. You would need some kind of way to tell your palm that the thing it is touching is in fact the body it belongs to, and to not try and damage it. The same may have been true for the ancestors of Dileptus and other organisms that have toxicists. They may have kept accidentally hurting themselves over and over, often beyond repair, until evolution provided a new path, one where they would be able to recognize themselves, and perhaps eventually, even others of their own kind. Thank you for coming on this journey with us as we explore the unseen world that surrounds us. And thank you again to Ren for sponsoring this episode of Journey to the Microcosmos. Ren is a website where you can calculate your carbon footprint and then offset it by funding projects that plant trees and provide clean-burning fuel and cook stoves for refugees in Uganda. We will need a lot of different approaches to stop the climate crisis, and this is one way that you can learn more about your carbon contribution and take some action. You can answer a few questions about your lifestyle so that you can see what your carbon footprint is, and they'll also show you ways to start reducing it. Now, no one can reduce their carbon footprint to zero, but using Ren, you can offset what you have left. Once you sign up, you'll receive updates from the tree planting, rainforest protection, and other projects you support. And we have partnered with Ren to protect an extra 10 acres of rainforest for the first 100 people who sign up using the link in our description. There are now a bunch of names that are coming up on the screen. These are our Patreon patrons. If you like what we do here at Journey to the Microcosmos, these are some of the folks that you can thank. And the good news is that you can become one of them. All you have to do is go to patreon.com/journeytomicro and become a Patreon patron. If you want to see more from our master of microscopes, James Weiss, you can check out Jam and Germs on Instagram. And if you want to see more from us, there's probably a subscribe button somewhere nearby.